for sure. So I'll wake you up with some jokes. But my overall teaching philosophy is joyful learning. Joyful learning is a buzzword, which means that my goal is to make you learn happily. You should be happy learning what you're doing here. My goal is not to fail you in the class. My goal is not to give you hard problems just for the sake of, but they are components of teaching which are needed to ensure that what you're learning stays with you. So those are the 7 things I usually follow. So I take all types of students. I know that in every class there are students who have different aptitudes. So there's some would be slow, some would be fast. So what I typically do, fast learners is okay. They can understand it really quick. And if they have done something, I give some extra questions on the side, or I bring a printout and I say, okay, you've understood, then you try these harder problems. But my goal is to get the slowest person in thinking to come on board and understand in the class, which means that if you're not asking question in the class, then I am not teaching well. So you have to ask question and don't be shy. Sir, I think a little slowly. No, you don't. You think fine. You ask me a question and I'll repeat it for you. So that's the one thing which you have to keep in mind. If you're coming and spending an hour, you take away what I'm trying to tell you. Second thing is, of course, this is my strength, that I break hard concepts into small and I present many different ways, which you'll see. I don't have to tell you. Also, I lay emphasis why you want to study something. So, for example, we are studying different parts of optimization. So, we'll see what real life applications are there in that. The fourth part is that this is something which students like is, I use Google Drive to upload everything and lectures on YouTube. So this is the Google Drive which I've shared with you. Admin is nothing, but this is something which I shared with you at the start of the lecture. This is that Neminath and me will teach this way. So there is nothing new here. Your student list, you guys know everyone. This is more for administrative purposes. So there are 2 more main things which you have to follow. One is the interaction where we do lecture, tutorials and labs. So everything will be uploaded here. So these 2 lectures are already there, I uploaded. So this is for students who want to read before coming to the class, that what is going to come up, let me be prepared. So if you don't study, doesn't mean that you will lose in the class, but some students want to study before the class. So you can, go over the notes, they are self-contained. And of course, after the lecture, you can go in. So in my class, if you don't want to write, that's also okay, but do bring a paper and a pen, because I'll make you do problems, which means that you have to scribble something to work something out, because there is a lot of math in optimization. So you can't do everything in your head, you have to write on a paper. So bring paper and pen. Then I upload tutorials also before the, so there are 2, this one is not needed. So tutorials also I upload before the tutorial when it happens. Tutorials will typically do it on Friday. TAs do the tutorial, but how well it is going, you can tell me. Hai na? So the questions are there, and then this is for the lab. The lab papers are already there. Those who were there in the last lab, I told that these are sample papers which you have to search for. Hai na? So that's about the drive, about the interaction. Then there are offline learning, which I call it as. So these are the recordings which we upload on YouTube. Right now it's not, nothing is there, it's a link to the lectures and all, because but I'll show you my lab page where the recordings are all there. Then there is supporting material. So for the moment I have uploaded these chapters from a book called Matrix Analysis by Karl Myers. So matrix inverse, in case you have forgotten it, in your linear algebra you can refresh it. Vector norms, most of you know, but I've still uploaded. Matrix norms, sometimes you get confused, so I've told you what different kind of matrix norms are. And then what is a positive definite matrix? Did Neminath go over this part? So in case you're confused, it has a whole chapter on it. Huh? So this is offline learning. Then as we go along, tutorial problems are not sufficient enough, so you give you practice problems, questions and solutions which you can work on. So we'll keep putting it as we go along. And then the exam part is, we'll take 1 quiz, as I said earlier. So as soon as the quiz is over, I'll upload the solution. As soon as the end sem is open, I'll upload the solution. This folder is not for you. You'll not see this folder. Great. This is my part where I'll have to upload it. So I'll just show you my mods lab, how the lectures are cataloged. I'll show you for which I just taught math of AI ML I taught this semester. And I'll show you my page, which is recording is done here. So So this is how a playlist is there, but if you go to my home page, you can see I've made all these playlists public. This was the last false optimization lectures. I taught the whole course. This time I'm sharing with Neminar. So in case you want to see earlier lectures also, you can go here and click the playlist. And
No,
you can see
I don't
all
need
the
a term
lectures.
plan. It's a waste of money, yaar.
So this was the Google Drive and PDF. Okay, now coming to evaluation. I'll not take 3 quizzes because we don't have time. Evaluation is important because unless you prepare for an exam, you will not, the material will not sink into your mind. You know, if I say there's no evaluation, then you, as soon as the semester ends, you'll forget everything. So evaluation is for that purpose. I'll grade leniently, but doesn't mean everybody gets a double A. There is a 15% of bracket provided by the academic office, so I don't grade harsh. Sixth thing which is very important is unstructured project. So now that you are in an advanced class, you're in the 3rd year. So this unstructured project, which we'll see more in the lab today, I want you to pick up a research paper and try to understand it, implement it, extend it. That is what the goal is, and there are 2 parts to it. One is writing the proposal and then writing the report. So that is how you will get evaluated in that. And this is something is the most exciting part, because the class is more of something which has been there for 20, 30 years, you know, in books and all. We're trying to teach you those concepts. The research papers which you pick up is more state of the art. And it also gives you the flexibility of picking a domain which interests you. Like those who were there in the lab last time, I said you can put finance, you can put automotive, you can put aerospace, you can pick civil engineering, whatever domain, or you can pick humanities for that matter of fact. It's not that you just have to do that. You can do social sciences, you can do game theory. Everywhere there is optimization. So pick an area which interests you and then try to understand that paper, and that will feed into what I'm trying to teach you in the class. So the class is going this way and this is complementing your learning. So that's the goal. Last thing is, now that we have started the lectures, almost half the semester is over. I usually take feedback and informal, where I ask you to scribble on a piece of paper what is going fine and what is not. And the goal is for me to adapt to you. Every batch is different. So we'll do that. We have 6-7 weeks, 2-3 weeks down the line, you tell me. The typical feedback which I get is pace is slow or fast, that's okay. But I need more practice problems which I typically upload. They say TAs are not doing a good job, they do go slowly on the tutorial, they go fast, I'm not able to understand. But if there's something in the class which I can make your life better in terms of enjoying the class, then we'll definitely do. Another thing which I do is not written here, is I crack a joke in the middle of the class. So I wake people up. I don't throw chalk, you know, to wake, like in the school you may have seen people throw chalks to wake students up. But that's the goal. Okay. Alright, so that's the part, and I think grading part I already discussed, but open it one more time for you. So there is one quiz which I'll take. 40% NSEM has to be there, so there's no choice. And quiz will not be a surprise, I'll tell you beforehand. It'll not be here, because if you do it here, you'll cheat. So we'll do it in a bigger classroom. And then for the lab, the grading is 25% project proposal and report. So we'll talk more about this in the lab. Hai. So what you have seen with Neminath is introductory math, and you have also seen unconstrained optimization. What you'll see with me is constrained optimization, which I'm going to start today, and then the other part is linear and nonlinear programming. So that is how we're going to do. So part 3, constrained. Okay. start with the introduction. We'll first write the standard form. Minimize f of x. F again going from an Rn to an R1 space. Subject to ai of x equal to 0. Cj of x greater than equal to 0. I is 1 through R, j is equal to 1 through S. There is some assumptions here. Ai, x and Cj of x belong to C2. And then R is equal to feasible region, which is defined by x with ai of x equal to 0, cj of x greater than equal to 0, I1 through R, j is equal to 1 through S. Okay. So there are three definitions which we'll write because we use them later. And then we'll also see how to convert one to the other. So a point x is a regular point of 1 if it satisfies 1 and column vectors a1 x through ar of x are okay. So we start now constraint optimization. An interesting thing about constraint optimization is that real life most of the things are constraints. There's rarely something without constraints, first of all. But sometimes it's possible to convert a constraint optimization problem to an unconstrained one, which we'll see. There's also a case where you would want to convert an unconstrained problem to a constrained problem. So I want you to think about this and tell me on next Thursday, or use your Google and find it, if you can find a problem. So everybody agrees that you would want to constraint as more challenging? Everybody agrees? Because there is a feasible region to worry about, right? Your solution cannot be in all over the space. It has to be in some space which is called the feasible region, defined by. So this is fx, n to 1, 1 to r, 1 to x. Both the constraints are C2. We assume it for a reason. They are continuous up to differentiable up to the second derivative, and that derivative is continuous. That is what it means. This is the feasible region. So what I am saying is, in the constraint case, you have to worry about the feasible region. So it's always more challenging. We'll see cases where we try to simplify, convert a constraint problem to unconstrained, and see if we can apply the basic steepest descent and Newton. But there would also be a case where you would want to do the opposite. You may want to convert a unconstrained problem to a constrained problem. So you find such a problem for me. Okay, this is your homework. Everybody, you can discuss among yourself. There is nobody stopping. But what could be the reason? Can anybody think about it? Why would you want to go the opposite direction?
It is theoretically possible, but practically it's not possible to get those area values.
Practically, what not?
It might not be possible to achieve those values, so we constrain it to some.
Okay, I'll give you a hint. When you convert from an unconstrained problem to a constrained problem, you get nice functional properties. Nice functional properties that your unconstrained problem has an objective function which is not continuous. It is not even C0. But when you convert it to a constrained problem, it becomes C infinity. C infinity means it's differentiable up to the nth derivative. So such a nice problem. So that's the reason you would do, that you're getting a better function in minimizing, but now you find such a function for me and tell me next Thursday. Huh? If I Okay, so we'll write 3 definitions here before.
When we convert to unconstrained problem.
Mhm.
This was the case when we do unconstrained.
No, this constraint to unconstrained, so you would do anyways because you are making things simpler for you, right? You are not worrying about a feasible region. So your solution can lie on all over the space. But I'm asking a case where you would go the opposite. From unconstrained to a constraint means you are increasing the difficulty of the problem. So a reason why you would do a hint is that the function which is not continuous in an unconstrained sense, the objective function, when you make it constrained, it becomes C infinity, infinitely differentiable and continuous. So it gets a very nice property. Now you can plug anything and do. But you find me such a function. That's your work. Okay. Coming back to constraint, we'll write 3 definitions. One for equality constraints, another for inequality constraints, and we'll also see whether we can convert the inequality to equality before we move forward. And we can make this simplification also. So first definition is about equality constraint. So this is equation number 1. So it says a point x is the regular point of x if it satisfies this, and the column vectors which are the gradients of these individual AIs, they are linearly independent. Now the question for you to think with me, what will be this definition in terms of the Jacobian of A? What is Jacobian of A, Yatharth? Right. So if I have to write Jacobian of A of x, what will be, Yatharth? All the way till del A1 over xn, del AR over x1 to del AR over xn. Yes, everybody agrees with Yatharth? So now tell me what property should the Jacobian of the A should have for x to be regular?
Non-singular matrix.
Non-singular, but what is the dimension of the matrix?
N cross N.
Sorry?
N cross R.
So the number of rows are R and the number of columns are N. We can write this here that R comma S both are smaller than N. Usually the constraints run, the problem dimension runs into millions in real life. Constraints may runs into hundreds of thousands. So they are usually multiple order of magnitude less than N. That's a general trend. So what is this matrix? Is it a overdetermined, underdetermined system of equation? What is it? It has less rows and it has it's a rectangular matrix. Singularity of a rectangular matrix you have not studied, right? You don't know whether to invert a rectangular matrix. You have the concept of pseudo inverse which we'll learn, but as of now you don't know. So what else can you say? You're on the right track, Krish. Sorry?
There will be rank of the
Rank, right. We are motivating it to rank. So this is saying the gradients are linearly independent. If I have to write the Jacobian of this, I would also write this as A1 transpose all the way till AR transpose. Transpose because I am putting the column vectors into row format. So the rank of this should be full, which means that it should be R, because then these row vectors would be linearly independent. Is this confusing you, rank discussion? Anybody not? You should have learned in your linear algebra course. If not, then you can go ahead and revisit. We'll be computing ranks couple of times now in the constraint optimization. So instead of saying that A1 to AR are linearly independent, we say the Jacobian of the A matrix is full row rank. Or full ranked, not even row ranked, it's full ranked. The second thing which we are going to learn is about the inequality constraints, and then we'll see how to convert inequality to equality. That's the third thing we'll see. Okay. So active and inactive. That is the concept. This is the concept which is going to run for the next 4 weeks because we're going to use this again and again. Let's say I've got C1 of x, C2 of x, C3 of x. These are my 3 functions of the inequality constraints, for example. And this side is C1 of x greater than 0. This side is C3 of x greater than 0. And then this side is C2 of x greater than 0. All of them in the standard form, C should be greater than equal to 0. If it's written less than, then you bring it to the other side and work with it. So now
this
if I...
is greater than 0, other side of C2x will...
So this would be less than 0, this is greater than 0, this is equal to 0, this will be less than 0, right? Those are only 3 options for every constraint. Everybody okay? Yes? So now if I say I have a point here, some point x1 let's say, which constraints I'll say is active and which is inactive. So I am right in the region of strictly greater than for C1, so C1 is inactive here. Again I am in the region of strictly greater than for C3, so this is inactive here, but I am on the boundary for C2, so I am active here. Okay, that's the idea, and this will come in our algorithm development because it will come in our necessary and sufficient conditions, which we're going to derive equivalent of what we have seen in the unconstrained case. Then when we start deriving algorithm, we'll have to worry about which are active, which are inactive to reduce our complexity of the problem. Everybody okay? So in this one, C1 and C3 are inactive at x1 and C2 is active. Okay. Now we go to the third thing which I wanted to tell you in the introduction, inequality to the equality constraints. Can we convert that? Okay, so we'll do it with a problem. Or let's do one example, or we'll do it at the end. So let's finish this conversion. So you've got minimize of x1 square plus x2 square subject to x1 plus x2 greater than equal to 0. Okay. So now your question is, can you convert the inequality constraint to equality constraints? How?
To introduce another variable and
Okay. So what do we do? x1 plus x2
plus x3, let's say,
plus
x3,
Mhm.
and we define it to be equal to 0.
Okay.
And then we say that x3 is greater than.
But then it's still inequality, right? You have to force it that x, in this case, if I say I make it equal to x3, then I'll have to say x3 is greater than equal to 0, right? Still an inequality. I want to completely get rid of the inequality.
It should not be greater than equal to, or there should be no greater than it.
No inequality means greater or less than sign. So I want to get rid of that. I just want to work with the equality, right? Anybody at the back, girls? What is your name? Yeah. Huh? Shravanti. Yes, Shravanti. What do you think? I'm just trying to learn name. Yeah, go ahead.
So we can define some variable such that we have a square term.
Right, exactly. So you can always say that x1 plus x2 is x3 square. We'll worry about later whether x1, x2 turns out to be negative and x3 gives you an imaginary value. But I can always write. So this thing is always greater than equal to 0. So earlier your x had x1 and x2. Now your x will have 3 terms, x1, x2 and x3. You're minimizing the objective function remains the same, x1 square plus x2 square subject to x1 plus x2 minus x3 square equal to 0. You increase the problem dimension by 1, but you were able to eliminate the inequality. Everybody okay? So you can do this in a general sense also. And I'll write that down. Before I write that down, I'll let you do one problem on the side.
So the figure which we have, the active and inactive constraints.
Mm-hmm.
So like if we have a graph, what is the variables?
One second, I'll come to you. Just let me finish what my thought is. Okay, I'll write the general form of converting to inequality to equality. In the meantime, you find the rank of this and tell me how you found it. I'll come to you, Sonu, hai na? Let me finish this.
C2 is only on the verge of getting violated at extent. They are already in the region where x1 and x2 will not be getting violated, and only C2 will be violated if you go in this position. C1 and C3 won't be getting violated, and C2 can be violated. Rank is 2.
Okay. Did you do this or you're writing with me? What did you do? You will convert this into the upper row echelon form, which means you want to make on the left bottom part as many zeros as possible. The number of non-zero rows in the upper row echelon form would be the rank of the matrix. So you'll make this guy 0, and then once you do this, what will come? So if you do R2 is equal to 8 over 9 R2 minus R1 to make this guy 0, then you'll get 8, 3, 6, 0, 32 by 4 minus 3, 64 by 9 minus 6, and then you can't make this guy 0 without making this non-zero. Similarly, you can't make this 0 without keeping these two as 0, which means that the rank is 2 because the number of non-zero rows in this form is 2. Everybody okay? Alright. Now let's look at the general form of converting from inequality to equality. So same, f of x subject to cjx greater than 0. We introduce slack variables with yi's with respect to every constraint. So we call c1x minus y1 square, c2x minus y2 square, cjx minus ys square, cs x minus ys square. So your new function becomes, so what is your x hat now? What is your x hat? x1 to xn
and xn plus 1.
and y1 to ys. These are augmented together. So you have minimized f of x hat, means now f is going from a n plus s space to a one-dimensional space, and Cj of x hat is equal to 0. Everybody okay? All right. I think we can stop here now. 4:25. So the next thing we'll do is classification. We'll classify the unconstrained problem, and then we'll do a lot of conversion from all sorts of unconstraints to all sorts of constraints. And your work is to tell me all sorts of constraint to unconstrained. Your job is to tell me the other direction in example. Okay? Yeah, your doubt. Okay, sorted.
So only one more thing, like C1x, C2x, C3x, their coefficients of the variable, they will define this is greater than area, this is lower than area. So then we are plotting it down, that will.
Okay, hold on. 1 second. Sonu has a doubt, so let me clear this. Okay, so Sonu is asking how would the regions be defined. Let's say I've got this C1 of x as just a straight lines, x1 plus x2 is equal to 1. Put this 0, you'll get this guy, put this 0, you'll get this point. Now your region is defined as x1 plus x2 minus 1 greater than equal to 0, right? So which region will it be, Sonu? Will it be the region below or above? Above, because simply check, put 0, 0 and see what happens. So now if I have to check, let's say I give you a point 1 and then here I give you a point 2. So at this point, this constraint is inactive. Understood, right? So that is how you would do. So at 1, 2, if you put 1, 2, it will turn out to be strictly greater than 0. 1 plus 2 minus 1 is 2, which is strictly greater than 0, means this constraint is inactive at that point. If I gave you a point here, then that would be active. And then in the tutorial, you did the two quadratic interpolation problems and you did a transformation problem, which actually I thought of doing in the class, but I let it do in the tutorial, where you given a LP in the standard form, not in a standard form, how we would convert it. Everybody was comfortable with those two problems on LPs? Okay. So we'll go further beyond that. So we are on in constraint optimization. We did the intro, which I just summarized it for you. We'll do classification today. And then what we'll do is transformation, which is going to take a lot of time. And then we are going to start with the necessary condition for minima. And this is where our friend, another friend comes. All French people are a friend for this course. The Taylor was also French. Lagrange is another guy who did a lot of work in optimization, and he would be our trump card here. So if you've taken optimization and don't know what Lagrange has done, means you have not studied well. So you should know Lagrangian, Lagrange multipliers and all kind of things. Okay. So this is done. We start with classification. So in classification, we'll first write the definition. So, so we say point x star is a global minimizer point x star is a global minimizer if Can somebody help me now? We did this in unconstrained. Everybody know that f of x star should be less than f of x or x belonging to all of the real spaces, Rn or whatever. What will change here now?
X star follows all the constraints.
Right. So x star belongs to R. This is not within R is the feasible region which we wrote last time, and f of x star. I mean, or you can write in a set format that it is smaller than all of fx in the feasible region. Okay, now if I have to write the same thing for the local minimizer, we'll say point x star is a local minimizer if there exist. Can somebody tell me? Okay, I'll write the ball part. If there exists a ball x star or the neighborhood x minus x star norm is bounded by delta, means there is a neighborhood with delta greater than 0 such that, now tell me what should I write?
F of x star is minimum of f of x and x belongs to the neighborhood of x star.
Right. So such that is minimum of f of x belong to
Ball as well as
The boundary of x star.
right. So that's important. If I write just boundary here, the ball, sorry, or the neighborhood, you want to call this as a neighborhood or a ball surrounding x star, right? By the way, there was a comment on visualization and n-dimensional visualization. The n-dimensional visualization is very difficult, but that concept will be covered when we take practical problems from your papers, because people, they do more visualization, right? Okay, so if I write this is wrong. Why is this wrong?
Because Ex star can go outside of R.
Outside of the feasible region. So if, let's say, you know, this is my feasible region, the ball which you are making of d dimension is running out of the feasible region. So you have to first find the intersection of the feasible region and that ball, and you should be minimum in that region because you are not defined outside that, right? So we'll write such that there exists an overlapping region which is B of x star intersected with R is non-empty. This is also important. If it happens that, you know, x star is somewhere here, feasible region is here, and you keep creating balls around here, it has no meaning. I mean, it should be feasible first. So it should be non-empty and it should be minimum in this intersection of the ball and the feasible region. Everybody okay? Sorry?
The X star should also belong to the feasible region.
Well, that is implied.
That is, I can take delta to be large enough to like have it intersecting if it's not belonging to R.
I mean, this should belong to feasible region. Otherwise, it's not considered useful for you, right? What will you search for? Okay, so what we do now, the classification was linear program, which I think by now you know. C transpose X subject to Ax equal to B, X greater than 0. You can sometimes, of course, here you know F is going from an Rn to R space. C of course has to belong to Rn so that they can multiply. A has a dimension small r cross n, and then the B has to be small r for it to match. Okay. Sometimes you write the linear program as transpose X subject to ax greater than equal to b. This is what Saurabh did in the tutorial and convert this into the standard form. How did you do it?
So vector x is x minus.
First you said ax minus b is equal to y, so that is one condition. Y is greater than 0. But now you need the x also variable to have all positive constraints, because that's what the standard condition says, that the input variable in the linear program should all be positive. So you split it into x plus and x minus and then do the rest of the computation. Everybody remembers?
Yes.
Okay. Give you one more, you do this. I think you did not do this with Saurabh. Or we'll do it for the quadratic.